just in case. All right, so this time I can't just take my speed and multiply it by my time because my speed's not constant. That wouldn't work. So let's look through and see. The graph to the left shows the velocity of a car carrying a crash dummy. What is the velocity of the car at t equals 3 seconds? So what would the velocity of the car at t equals 3 seconds be? Okay, 16 feet per second. We're just looking at this point right here. Right, this is our graph of velocity. We're going to 3 seconds. We're finding the point, and we're given the y value there. So we would get 16 feet per second. Okay. The next question asks us for the acceleration of the car. What would we need to do? Okay, that would be our slope, right? Because if you remember back to those position problems that we did, we would have a function that was a position, and then to find velocity, we would take the derivative, right? And if we wanted to find acceleration, we would take the derivative of velocity. And a derivative is a slope of the line. So here, if we just try to find another place where we cross grid lines perfectly, it looks right there at 625 is good. You could probably find some others. That one feels pretty safe though, right there. So you could count it. You got the point 316. You got the point 625. So if we're looking for the slope, we could just do slope formula there. 25 minus 16 over 6 minus 3. And we are going to get 9 over 3. So 3. What are my units for acceleration? Feet per second per second. And if you're having trouble remembering what the units are, this is your change in y. This is your change in x. Here, whenever you do your slope formula, your y, your top number, is measured in feet per second because your y-axis is measured in feet per second. Your x-axis is measured in seconds here. So that would be feet per second divided by seconds. Feet per second per second. You could also say feet per second squared. Okay, now A and B are both questions that we have already talked about how to do, right? Those are, A is not technically even a calculus problem because you're just reading it off the graph. B would be a calculus problem because, technically since it's a straight line, you could have figured that out before you were in calculus, but that is more of a calculus problem. C asks us how far does the car travel in the first 7 seconds. So here, we're going to have to take the idea that I was showing you on the warm-up problem and expand it to what we're looking at here. So the first 7 seconds, I'll erase those, is up to here, which goes to this point right here. So it is going to be impossible for us to do like 7 times the velocity because the velocity is changing here. But if I find the area of this shape right here, when I'm finding that area, it is taking my time and multiplying it by my velocity, which is feet per second times seconds, which would just give me the number of feet that have been traveled. So, because this shape right here has all straight sides, I can find the area of that. You have some options on how you would find the area. What shape is that? Trapezoid. But if you possibly are rusty on your trapezoids, you could also just draw a line across here and you could make it a rectangle plus a triangle. That would work. If you're going to do trapezoid, what's the area of a trapezoid? You're going to need to know it. Yes, that's part of it.
Times height divided by 2.
Yes. Base 1 plus base 2 times height divided by 2. Or sometimes you'll see it 1/2 height base 1 plus base 2. It's one we're going to need to know because as we move along, it's going to be a question we'll see it come back up several times. So, so in this case, your bases are your parallel sides. So this right here would be a base. It would be 7. This over here, what is that, 28? I think that's 28 right here. Your height is this trapezoid's kind of turned on its side. The height right here is actually 7. Right, that would be our height there. And so we would do 7 plus 28 times our height, which is 7 divided by 2. And I think I'll just grab the calculator for that. It's not that hard, but let's see. And I'm getting 122.5. And that would be feet. So by finding that area underneath the line there, we're finding the distance that was traveled. Just another note on trapezoid formula. This helps me to remember trapezoid formula. Whenever you're finding the area of a trapezoid, what you're really doing is like cutting off this piece right here and this piece right here and adding them right here to make a rectangle. So to do that, like area of a trapezoid is average of the bases times the height. That gives you area of trapezoid. Average of the bases is base 1 plus base 2 divided by 2, and then you multiply by your height.
What are the bases? Like, I know there's 7 on this one, but wait, what are they like?
The bases are your parallel sides. So like on the trapezoid I just drew here, like that bottom side would be a base. That might be your base 1, and that top side would be your base 2. In the one that we just did, these two sides right here, so they're like vertical, and this side right here, those are your bases. It's got to be the two sides that are parallel to each other. Okay. On this one, you could just do a rectangle and a triangle. On some stuff that's coming up, you don't want to do rectangles and triangles. It would take you forever. You're going to need to know that trapezoid formula. Okay. All right, let's keep going. All right. So for this one, we have a different context. The graph to the right shows the rate at which the amount of water in a tank changes after t minutes. At what rate is the amount of water in the tank changing at t equals 3 minutes? So what would our rate of change of the amount of water be at t equals 3? First of all, we got to decide, are we looking for the point? Are we looking for the slope? Are we looking for the area? This one is just a point. Because while it asks for what is the rate the amount of water is changing, so it does want a rate of change, but the graph is the rate of change, right? So it's just the point. So at 3 right here, we get 6. So it would be 6 gallons per minute. Okay. For B, it says at what rate is the amount of water in the tank changing at t equals 6 minutes? It would be 8. Very good. You're looking at this point right here. It is 8 gallons per minute. It's the same question as before, but asking you for a different one. You might be prone to say 0 right there because it's flat, but that would be the rate of the rate, which is not what they're asking you for here. C, does the amount of water in the tank ever decrease? Okay, why not? It goes down right here.
That's the rate of change going down, so that just means like the amount of water going into it is increasing, but it's not actually increasing the level in the tank.
Okay, you're exactly right. You're exactly right. Because this is our rate. It's positive the whole time, right?
Yeah.
For us to actually see the amount dropping, right? For us to see the amount dropping, we'd have to see a negative rate of change right there. So like Xander said right here, the amount of water going into the tank is not as much as it was before, right? It's slowing down, but it's still got water going into the tank. So no. I'm going to just say rate of change is positive.
Can you ever tell, like from just this graph, can you ever tell how much water is actually in the tank?
We, on this one, cannot figure out how much water is in the tank because we don't know how much we started with. So there might have like already been water in the tank. But we're going to see here in a minute, we can figure out like how much has been added to the tank. So we can figure out like actually how much is there. So let's look at D first though. D says, is the rate of change of the amount of water in the tank increasing or decreasing at t equals 5?
I say neither, but also
Okay, why would you say neither?
because at that point it's in the middle of that flat area, so it hasn't increased or decreased like before or after.
Okay. I think I agree with you, but you used the word it way too much whenever you were talking about it, so I'm not sure if I agree with you.
At t equals 5.
So at t equals 5. Okay.
How to explain that, like, without, can you just say the acceleration is 0?
You wouldn't want to use the word acceleration here because that refers to like position, velocity, acceleration. You can compare it to, you can think of it as acceleration. Here, this graph is our rate of change, right? We want to know is the rate of change. We don't know what, in like A and B, we want to know what the rate of change was. In D, we want to know if rate of change, we want to know if it is increasing or decreasing, right? So we need to know, if we want to know if our rate of change is increasing or decreasing, we need to know if the derivative of rate of change, which would be our slope of the rate of change, or our rate of change of rate of change. We want to know if the slope of the rate of change is positive or negative. And, as Xander was saying, is our rate of change, our slope of our rate of change positive or negative there? Neither one, right? It's flat. You have a slope of 0. So at t equals 0, the rate of change. It is not good to put ROC on quizzes, tests, AP exam, but I don't have a lot of room to write here. So at t equals 5, the rate of change has a slope of 0. So the rate of change is neither increasing Now, E asks us how much water was added to the tank, right? This is the question that is like our new information, the stuff that we are just learning. Because if we think about finding an area, right? I know this is not like a rectangle, but we would be multiplying what's on our x-axis by what's on our y-axis. And when I multiply gallons per minute times minutes, right? That minutes I could put over 1, my minutes cancel, and it gives me gallons. That should be gallons, but I ran out of room right there. So, whenever I've got this last one, it says how much water was added to the tank over the first 10 minutes, I can find the area of this shaded region right here. Okay, so you've got some options on how to deal with this one as well. I would probably do something like this. If you want to avoid a trapezoid, I mean, you can make that a triangle right there. You could split it up differently if you want. That's fine. But if we find the area here, this is 4, and that is a height of 8. So we would be doing 1/2 times 4 times 8, which would give us 16 right here on that piece. This part would just be 2 times 8. That's also going to give us 16 for that piece. Here we would have 4 times 5, so we'd get 20 right here. And then here we would have 4 for this base. We'd have 3 for our height, so it'd be 1/2 times 3 times 4. We'd get 6 right here. So if we add all of those together, our 16 plus 16 plus 20 plus 6 is going to give us, let's see, that'll be 32 plus 26 will give us 58 gallons. Now this almost tells us how much water is in the tank. We don't know what we started with. The tank was empty to start with, and we've got 58 gallons. It's possible the tank already had 100 gallons in it. Now it's got 158. So we would have to have one more piece of information to know exactly how much water is in the tank. Okay, questions? Okay, so I have got a table this time. A drag car travels down a track. Selected speeds of the drag car are given in the table below. Here. And then it's going to ask us several questions here. So the first one says, what is the average acceleration of the car for the 2.5 seconds shown on the table? So if I want to know average acceleration, right now, this, like, if we think of graphing this, we've got speed here, which is not exactly velocity, but we can think of it like velocity, especially in a drag car situation where our car is just going straight down the track, right? And then we've got seconds here on the bottom. So if I want to find acceleration, am I looking for like just a point here? Am I looking for a slope? Am I looking for the area under the curve? The slope, right? So, it's specifically, if it's average acceleration for the 2.5 seconds, that's just the slope between the endpoints. So I got the point 0, 0, and I got 2.5, 145, which will fall right here. Right? So I'm just looking at like that slope between the endpoints. So if I've got 0, 0, and 2.5, 145, essentially I'm just doing 145. Technically there's a minus 0. divided by 2.5 minus 0. So definitely use the calculator for this. 145 divided by 2.5 is going to give me 58. I don't mean for that to be the same answer that we got on the last question, but it just happened to be. What would the units for that be? Very good. Feet per second per second. Yes, you can. It's okay to do 58 feet per second squared. Either one of those are fine. Okay. Now B asks us to estimate the acceleration of the car at 0.75 seconds. So we're still talking about acceleration. We're still talking about a slope. What are we going to do there? Right, so that would fall right here in between 0.5 and 1. So if we find just the slope between those 2 points, that's going to be as close as we can get given the information we've got. So we got these 2 points right here. We got 0.5, 60, and we've got 1, 110. And we're just going to do slope formula there. So we'll do 110 minus 60 over 1 minus 0.5. And that will give us 50 divided by 0.5, which will be 100 feet per second. Or feet per second squared. Okay. Now A and B are both problems we've already done. They're talking about slopes of graphs that were given. This is stuff that I could give you on, stuff we've already had. C is different. C is asking for the distance the car has traveled, right? So if C wants to know the distance the car traveled in the 2.5 seconds, now we're thinking about like area underneath this curve. But this is a different situation because we don't have like the equation exactly, right? So I'm going to graph these points. I think it's going to help us see what's going on a little bit here. So we got 0.5, 60. We've got 1, 110, 1.5, 130, 2, 140. Now, when you look at that, this looks like it's sort of like a concave down sort of curve, right? In fact, if we like drew it in, it probably is a smooth curve that looks something like that. Not perfect there, but probably looks something like that. So we would be looking for the area underneath that curve. Now, are we going to be able to find that exactly? We cannot. And not just because we don't know enough calculus yet, but also because they only gave us points. We don't know like the equation of that curve or anything like that. So, so we wouldn't be able to find the exact area. Any ideas how we could get like a decent estimate? Okay, what you were suggesting is not a terrible idea. Did you guys ever have to do that in like elementary school sometimes? Like they'd give you a weird shape and it was on a graph and you just counted the boxes and you were like, there, look, piece of a graph here, piece of a graph here. That's okay for this. Now, you do need to be a little careful because let's just use like the major boxes right here. You do need to be a little careful. Like this major box right here. How much is that? There are 16 boxes in it. It's worth 10. Why? Because the height of that box is 20 and the width of that box is 0.5. So that your scale on your axes makes a big difference here. So like if we're thinking about those like major major grid lines here. Each one of those boxes is worth 10. So if we kind of drew in those major grid lines here, we got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we definitely have at least 21 boxes, right? But then you're going to start, I'm going to say like these 3 together right here, that's probably 1. So there's 22. Maybe if I put like this piece and this piece together, there's 23. Maybe that's 24. 25. So they're each worth 10. So about 250 feet. Now, that's a guess. It's not perfect. If it was multiple choice, maybe it'd be close enough for us to get the right answer, but if you're looking for an exact answer, would be something better, right? So this is not a bad idea right here. It's not going to be perfect, but it's not a bad idea. As we go along, are going to learn some other methods for estimating. So it's, we're going to learn some more like precise methods for estimating. Sometimes they're still not very good. Sometimes this is just as good as doing that, but we will learn some more there. All right. Now, this question, I was about to say I think I'm not going to do this one, but then I remembered which question this is. And we have to do this question because I made this question probably on February 5th, the 4th or 5th, 2020. At this point, this is a moment in history right here. At this point, the coronavirus was a distant thing. It was in China. There were a few little news stories here or there. Little things. Oh, there's this disease in China and some people are sick. And it's not good. But at this point, Coach Wood's coming by my room. He's coming in. He's asking me questions like, Miss Hyatt, how many Coronas do you have to drink before you get coronavirus? We're all still here. Absolutely no idea that we were just about to get sent home from spring break and never come back, and then have to be going through everything we did. So I made this problem at this time. So I need to do it just because I feel like it's kind of crazy that I made a problem about it, and I was thinking about it, but I also did not think that like when I taught this the first time, I was like, it's probably going to stay over in China. It'll be fine. Don't worry about it too much. And then it just blew up. So at this time, very early on, these were the deaths per day, and everything was still in China. If it was out of China yet, we didn't know it was coronavirus. So all the people that you know that had pre-COVID COVID, I feel like everybody knows at least one person that was sick in January or February that year. I probably had it before it was even over here. So at this time, these were the number of deaths per day in China. Okay, so if we want to look at this, if it asks us from January 23rd to January 29th, the number of daily deaths increased at a rate of blank here. If we want to know what that is, then we would just need or the number of daily deaths increased at a rate of, oh gosh, let's see, from 23 to 29. We want, oh gosh, I don't know if I meant to ask that question that way. So the number of daily deaths increased at a rate. We don't want the slope right here because the answer to this is deaths per day, right? So we really just want to know, like, the like change in what has happened here, right? So it was 8 deaths per day. It went up to 38. I guess we just want an average of like 8 and 38 to get average. I think maybe I asked that question wrong. Let's change. I'm going to change the way it's written. Let's say the number of deaths per day. I think that's what I meant. This is probably something I fixed last year and didn't save the work. I'll probably forget to do it again this year. So, deaths per day. From January 23rd to January 29th, we're looking at the rate that it increased. Now it's asking us for a slope, right? So we would do, first thing I would probably do is you really need these to be in, like, not the numbers of the days, because we'll be able to answer A just fine, but B's not going to work because we switched months. So what I would probably do is I would let this day right here be 0. And so if 23 is 0, then 24, 25, 26 would be, wait, okay, 24, 25, 26 would be 3. And then 27, 28, 29 would be 6. This would be 7 right here on January 30th. Then you got January 31st, February 1st, February 2nd. So that's 3 more days. That'd be 10. And then this will be 12 right here. So let's make those numbers instead of dates, because the switch from the month is going to give us trouble. So we would have the 0.08 and we would have the 0.638. Okay, so we're going to do 38 minus 8 over 6 minus 0, and we would get 30 over 6, which would give us 5. And this would be deaths per day, So there, in the early part of January, like every day, the number of deaths each day was going up by 5 days. Between January 30th and February 4th, you would be looking at the 0.743 and 1266. So we do 66 minus 43 over 12 minus 7. And for that, we would have, what, 23 over 5, which is going to give us 4.6. And that would be deaths per day. And in 2020, I was like, look, it's not like getting faster. Maybe it's still growing, but maybe it'll slow her down and go back. But it's going to be a long time before that actually started happening. So if they asked us to estimate here, this we may not have quite time for, but we could do like we did on the last problem. We could graph all of these and like look at our area under the curve for that. I'm going to skip that because I want us to look at the FRQ and I want us to at least get our equations graphed for our activity that we're going to do. So I'm going to skip that part right there. But you should be sort of seeing, like, we've already talked about things where we need slope. Now we're going to start talking about that area underneath the curve.